The example of finding the center of mass of a car we did in the previous video is pretty basic. Let's take on a little more interesting example, a ladder leaning up against a wall. We're going to treat the wall as being frictionless because it simplifies things quite a bit. And really, it's probably not a bad assumption to assume that the friction force on the vertical wall is not a big part of what's keeping this ladder leaned up against that wall. The other forces that are preventing the ladder from slipping are probably far more important. So we want to find the forces acting on the ladder, and we want to find the minimum coefficient of static friction we need between the ladder and the floor to prevent the ladder from slipping. So this is a typical statics problem. We know this object is not moving, so we know it's in equilibrium. That means the sum of the forces has to be zero, and the net torque has to be zero. This is a dynamics lens. And the first thing we like to do with a dynamics problem is draw a free body diagram. So there's my ladder, and I ask myself, what's touching the ladder? Well, the vertical wall is touching the ladder. Because we're ignoring friction with that wall, it only has a normal force acting on our ladder. I'll call that N sub W for wall, the normal force from the wall. What else is touching the ladder? The floor is touching the ladder. The floor can interact two ways, through a normal force, N floor, and through a friction force, static friction, preventing the ladder from slipping out. That's everything that's touching our ladder. What can reach in from a distance? Gravity. And the force of gravity acts at the center of mass, and because this is a uniform ladder, it acts at the center of the ladder. Now we say the net force has to be zero. And I can break that up. Some of the forces in the x direction have to be zero, and some of the forces in the y direction have to be zero. And I can pick some coordinate system. So first I'll look at the x direction. I only have two forces in the x direction. The friction force with the ground and the normal force with the wall. So those two forces have to be equal in magnitude and opposite in direction to cancel out. Then in the y direction, I can see that the normal force from the floor minus the weight of the ladder has to add to zero because I have two forces in the y direction, one in the positive direction, one in the negative direction. I guess I should define a positive direction. There we go. Oh, I did. I did define a positive direction. Okay, so my normal force from the floor is equal to the weight of the ladder, and the friction force is equal to the normal force from the wall. Now we can do one more thing. We can say the sum of the torque is equal to zero. And we can say the sum of the torque is equal to zero about any axis of rotation we want. This ladder is not rotating. It doesn't matter what axis of rotation I pick. So I'm going to pick the one that has the most unknowns. The base of the ladder has the normal force from the floor passing through it and the friction force. So if I pick that as my axis of rotation, both of them will have a zero lever arm. They are both producing zero torque about that axis of rotation. I have to define a positive direction. How about into the page as my positive direction? When I add up all my torques, these two are both zero. normal force from the floor and the friction force are both zero torque. They have zero lever arm. I have the weight of the ladder that will cause my ladder to rotate in the positive direction. So I've got positive torque times its lever arm. And what's its lever arm? I extend the line of force, and its lever arm is this distance right here, the perpendicular distance from the line of force to the axis of rotation, d1. And I can figure out what that is because I know this distance is L over 2, and I know this angle is 53 degrees. So d1, the lever arm for the weight of the ladder, is equal to L over 2 times the cosine of 53 degrees. Now I look at the next force I have that's creating torque, and that's the normal force from the wall, and it's causing torque in the negative direction, and its lever arm is this distance here. I extend the line of force, and this distance, the perpendicular distance to the axis of rotation, is the lever arm. Now if this angle is 53 degrees, that means this angle up here is also 53 degrees. And I know the length of the ladder is L, so I know that d2 is going to be L times the sine of 53 degrees. It's the opposite side of that angle. And I add up these torques, and I have to get 0. So let me plug in. I've got mg L over 2 cos 53 degrees. And now I can solve for the normal force. I got 151 newtons. So I can go back and I can say, I've got two other expressions I can use. The friction force has to equal that, because the friction force equals the normal force with the wall. And I know the maximum friction force is going to be mu times the normal force. Well, which normal force? It's this normal force right here, because that normal force with the floor is what's creating this friction force. So we can put the weight of the object there. And the maximum static friction force, if we solve for that, that will give us the minimum coefficient of friction we need to prevent this from slipping. So we set these equal to each other. The weight of the ladder is 400 newtons, and we get our minimum coefficient of friction is 0.38. So one thing we know about an object that's not moving, it's in equilibrium. Sum of the forces equals 0, and sum of the torque equals 0. And the net force we can break up into x component that has to be 0 and a y component that has to be 0.